We have Adithya at Sandia National Labs. We'll be talking about data-driven compact models for circuit design and analysis.
So thank you very much for organizing this conference. Our project is about an important problem, applying machine learning to data-driven circuit design and analysis, which is essentially computer-aided chip design. So I work at Sandia National Labs, and this is joint work with Paul, Liliana, Pavel, Kenneth, Alan, Ting, and Eric. So a lot of people on this project. So let me start with the problem. The problem is there's a chip designer represented by Dilbert here. And the chip designer wants to design a chip that meets some very stringent performance requirements. Usually, the way chip design goes is you first design a candidate design. You don't know if this is the final design or not. And then you run this candidate design through millions and millions of circuit simulations for various inputs under various test conditions and so on. And if all these simulations find bugs in the design, what you have to do is you have to go back and fix the design. So there is this cycle over here. And eventually, after a few loops of this iteration and refinement, hopefully the circuit simulator will not be able to find any more bugs, and you have your final design. So what goes on inside the circuit simulator? So the focus of this project is in the circuit simulation aspect of this whole design flow. So what a circuit simulator has inside of it is a mathematical model for every single component that you can possibly use in your circuit. So you have resistors, you have diodes, capacitors, voltage sources, transistors, any kind of component that can go inside the circuit. There is a mathematical model for it that is already coded into the circuit simulator. And once the circuit simulator has these models for the individual devices, you can use the circuit simulator to predict the behavior of circuits as a whole that use a combination of these devices. So for example, this is a circuit that's got a diode and two resistors in it. And this is a different circuit. This is actually an amplifier that uses some resistors and transistors and so on. And so you tell the circuit simulator how each individual device behaves. And the circuit simulator can then use that information to try and predict how the circuit as a whole will behave. Okay, so the circuit simulator needs to know how each individual device behaves. So what does an individual device look like? Well, electrically speaking, if you take a device that's a transistor or a diode or something like that, it's got a bunch of terminals. So you can think of a device as a bunch of terminals sticking out. And these terminals, I'm just calling them 1 to n over here. Each terminal, if you have n terminals, you have n minus 1 voltages. So you designate one particular terminal as a reference terminal, and then every other terminal has a voltage with respect to the reference terminal. So these are the voltages, V1n, V2n, and so on. So a device with n terminals has n minus 1 voltages, and you stick these voltages into a vector, and in this case, I'm just calling this vector V. Now a device doesn't just have voltages, it also has currents. So if you have n terminals, you have n minus 1 currents, because all the currents will add up to 0. So you don't have to consider n currents, you just have to consider n minus 1 currents. And similarly, I denote these currents I1, I2, and In minus 1, and I stick them into a vector and I call it I. And there is a mathematical model that relates the currents to the voltages. So if you apply a specific set of voltages to the device, you will get a specific set of currents. Now, I should mention that in real devices, this is actually a differential equation and not just an algebraic equation like what I have written out here. But for the purposes of this talk, I'm just going to consider that I and V are related algebraically through a nonlinear function, which I call F. And this nonlinear function is essentially what is known as a compact model in the industry. So this is a mathematical model for how each individual device inside a circuit behaves. And because both V and I are n-1 are vectors of dimension n-1, this F is a function that takes that goes from R n-1 to R n-1. So this is what a compact model is, a function that translates voltages into currents. And this is what is used inside a circuit simulator. Now, if you look at real compact models in the industry, they are extremely hard to develop. So for example, the canonical example here is a BSIM compact model, which is essentially a model that describes how modern MOS transistors work. And if you look at the BSIM model, it's got 644 equations in it. It's got 5,400 lines of code. And there is this entire team of grad students and postdocs at UC Berkeley, which has been working for 20 plus years on developing a sequence of compact models, and this BSIM CMG is the latest model in this sequence. So developing a compact model from scratch for circuit simulation is not a trivial task. And in this project, what we essentially want to do is we want to use machine learning to try and develop these compact models. And the way that's going to work is we have a large number of devices in the lab. So let's say we have 100 transistors or 100 diodes. Now we can stick voltages across the terminals of these devices and measure the currents. So we can just take these devices, apply whatever voltages we want to the terminals, and measure the resulting currents. And so we use lab equipment to essentially measure these the parameters of these devices. And so we can collect a large amount of data about these devices. And then the hope is that we can use machine learning techniques on this data to try and automatically come up with compact models. So at least, if not fully automatically, at least automate a big portion of compact model development. So that is the goal behind this project. And there are three techniques that we have applied to this problem. So one technique is called table-based interpolation. The second one is called generalized moving least squares. And the third one is deep learning through deep neural networks. So let me just tell you a little bit about each. So table-based interpolation is something we are all familiar with. It's just you have this data. So here, for example, I have V, the voltage on the x-axis, and the current on the y-axis. And I have a bunch of data points that I have collected by measuring a device in a lab. Those are the orange points here. And what I do is I just fit a multidimensional spline to this data to try and obtain a compact model for this particular device. Now, the advantages of this method is it's simple and straightforward. You just have to fit a spline to the data. But the disadvantages are, well, first of all, if you're going to fit a multi-dimensional spline, the most straightforward way to do that is if you have data on a rectangular grid. If you have data that doesn't fall on a rectangular grid, then you have all kinds of other problems in fitting splines. The second problem is you have to store all the spline coefficients, which consumes an enormous amount of memory. Now, these compact models have to be really, really efficient because modern chips have millions and millions of transistors in them. And if you want to do a simulation on a modern chip, you have to be really, the individual model for each transistor has to be really efficient to evaluate. And so this table-based interpolation fails that second test. There's this technique called generalized moving least squares, or GMLS. The key idea here is you have a basis, a set of basis functions. I'm just calling them G1 to Gn over here. And what we do is we try to approximate this f that we want as a linear combination of these basis functions. And essentially, given a particular vector v, we want to find the currents, which is f of v. And every time we have this vector v, we solve a least squares problem to determine these coefficients. And that gives us our approximation to the function, which is our compact model. The pros are this method works for scattered data, and it's got lower memory consumption than splines, but it still consumes a fair amount of memory. And this least square solution can become expensive if you're doing it millions of times. Which brings us to the third method, which is the deep neural networks. So essentially what we are trying to do is trying to use deep learning to learn this function f, which is our compact model. The pros are this is very CPU and memory efficient, simply because if your network is small, you just have a few activation functions and weights, and that's all you need to represent in memory. So it's very memory efficient. But the problem is it's very hard to get right. By that, what I mean is, even if you have a function that seems to capture the device characteristics pretty well, what we found is that if you try to implement this function and throw it into a conventional circuit simulator, what happens is the circuit simulator internally uses a method called Newton-Raphson to solve the circuit equations. And most of the time, what happens is, if you're not careful, the circuit simulation will fail. And that's because this Newton-Raphson will refuse to converge. So we have 3 tricks that we figured out for getting around this problem. The first trick is to transform the data. So instead of just taking this vector v and trying to learn the vector I from it, what we found is that if you take a transformed version of v and try to learn a transformed version of I, this can work much better than the original problem. And that's because this is a multi-scale data. So the currents in a device, in a typical transistor, for example, can vary over several orders of magnitude. You can have currents that go from, say, one femtoampere to maybe 1 microampere. And so to capture data over this wide range, we found that applying some transformations, especially logarithmic transformations. The second trick that we found works is to enforce physical constraints like monotonicity, passivity, and so on. So monotonicity just means that if your voltage increases, your current cannot decrease. And passivity means that either a device consumes power or a device supplies power. So devices that consume power cannot supply power. So if you incorporate these kinds of physical constraints into the learning, that really helps with the circuit simulation convergence. And the third trick that we learned is to use to do extrapolation the right way. So for example, let's say that your data falls inside this gray box over here. And so in the course of a circuit simulation, you can query the data at this vector v here, which is well outside this box where the data is. And neural networks are generally very bad at extrapolating data to points that are well outside the extrapolating to outside the range of the available data. So what we do is
just a minute left.
Yeah, I'm almost done. So what we do is we take this point v star, which is on the box, and then we use this kind of a relationship to extrapolate the data based on evaluating the neural network only on the box and not at some point well outside the box. So that's the end of my talk. So I'll be happy to answer questions.
Thank you, Adithya. And I just want to say that I appreciate your hand-drawn slides. They're very nice. You're inspiring me to go back to that. So one question that was asked is, have machine learning techniques been explored also for the discrete part of the circuit design?
So what exactly is the discrete part of the circuit design? Can you clarify that a little bit?
The person who asked the question, it didn't clarify, so I'm not sure.
Okay.
If you're not sure, then I'll ask a different question.
Okay, sure.
So I like how you have one of your approaches is to just fit a multi-dimensional spline to the data. I have colleagues in the math department ask me that often about modern machine learning and why not just fit multi-dimensional splines to data instead of using these deep neural networks. So, I mean, that's quite different from then the neural network approach you mentioned. Can you just briefly comment on sort of which you think is more promising?
Well, if your data set is small and the number of dimensions in your data set is small, then a multi-dimensional spline can work very well, simply because splines are easy to evaluate, and they do consume a lot of memory because you have to store all the coefficients. But if your data set is small, then that's not a major concern. So they work well in those situations. And the other thing is, it's really easy to get a spline to converge with a circuit simulator. With deep neural networks, the problem is they don't work so well in circuit simulators unless you're very careful about constructing the model. The circuit simulator very often fails to converge. But if you get it right, they can be very fast and very memory efficient. So you have these trade-offs here.
Adithya, one more question. Someone asks, electrical circuit models are often ODEs. Did you ever consider a neural ODE or something similar?
Just to not to put too fine a point on it, electrical circuit models are generally DAEs, not ODEs. So right now we are trying to capture the what is known as the steady state or DC behavior of electrical devices. But eventually the plan is to capture the transient dynamics as well, which is where the DAE component of it will become important. So that is something that is definitely on the agenda, but we have to sort of crawl before we can walk.